மாலத்தீவு படமும் இவங்க கலையை நடந்து இங்க வர சொன்னாங்க பசங்களுக்கு. மேடம் யூடியூப் நீங்களும் வந்து ஜாயின் பண்ணிச்சோங்க ஃபேக்கல்ட்டிக்கு நான் அனுப்புறேன். தக்க வச்சிருக்கு வணக்கம் ஸ்டார்ட் ஆகி நாக்க வணக்கம். கலைமணன் கூப்பிட்டு கலைமணன் கூப்பிட்டு 2 பேரும் கொஞ்சம் பசங்க என்ன அவன் எங்கிருந்து வேணாலும் ஜாயின் பண்ணிட்டான். அசைன் பண்ணா போதும். வராங்களா? சேர் வேணா 2 போட்டுருங்க தனியாக உட்காந்து. பிளாஸ்டிக் சேர் 2 நான் கொடுத்துருங்க உட்காந்து 2 பேர் ஃப்ரீயா இந்த செஷன் அட்டன் பண்ணுங்க மேடம். குவாண்டம் கம்ப்யூட்டிங் நான் லிங்க் குரூப்லயும் வைக்கிறேன்.
మాట भाई
Anybody know Akulapa number?
Hello.
Give me that mobile phone. Hello, Akulapa. Not in speaker. Hello, Akulapa.
Hello. Listen, all the students.
Hello, Akulapa. Wait,
Mute your
okay.
voice and
Teachers
video.
from other college have to get information. Don't create any bad impression. Why not? Mute it.
ఏమే నారాతో అక్క హాయ్ చెప్పండి
Hello, madam, have you joined?
Yes, sir. 1 second, sir.
Okay, madam.
Yes, sir. Yes, sir.
Madam, can you share your PPTs?
1 second. Sir, can I give permission, sir? Hello?
Madam, I will make you as a co-host.
Okay, sir.
Check it now, madam.
Yes, sir.
Yes, madam, now it is visible.
Yes. Okay.
Okay, I'll just officially introduction will be given. Then after that, you can start, madam.
Yes, sir.
So, dear students, last week you have attended the very introduction about the quantum technology system. Now, the third module, building a quantum computer, theoretical challenges and requirements. Under this topic, presentation will be started now. Dr. M. Dhanalakshmi, professor from CSC department, RV Institute of Technology. Madam will continue the session. Until completion of the session, do not unmute your audio or video unnecessarily. In case if any questions raised by madam, then only you unmute it and give your answer. Or if you want to raise any queries, raise your hand or unmute and ask your doubt. Okay, so it is like a pure interaction session. So you can raise your doubt. And today, for the today's session, I would like to welcome our resource person, Dr. M. Dhanalakshmi, madam. Now the session will start. Madam, the session is handed over to madam. Madam, you can start.
Okay. So, good morning, everyone. Last class, we were just discussing on introduction to quantum computing. We came to know why we should presently we should focus on this quantum technology. As we know that in the current trend, we are working on ML and deep learning, and these are working on classical computers like CPU and GPU, and when you focus on this GPU, particularly when you're working in deep learning, as the huge data set increases, the training time, it will take more time requires to train the model, it will become more. And then since this GPU is supporting for us to work on large data set, since it is on for huge time, the system may generate more heat. And because this GPU feature is that it supports massive parallelism, because of these reasons, what we are trying to do, we are focusing on much faster computer we need, because we want to process more huge data set. As the data keeps increasing in the real world, you know that in the cloud, in the big data. So since we want to handle more and more data, definitely when we design any model, we need to train the model on more and more huge data set. Then definitely we should focus on faster computers. So that is why we are going with this quantum processor unit. Now, today we are focusing on module 3, that is building the quantum computers, theoretical challenges and requirements. Yeah, so before focusing on how to build this quantum computer, we have to just look around how we build the classical computers. There, what we did, the basic, if you focus on your CPU chip or your GPU chip, that they are made up of gates. Okay, that gate internally, if you see, it is made up of transistors, and your transistors can off state, on state. Your off state can be represented by 0 bit, and your on state can be represented by 1 bit. And thus your CPU understands only zeros and ones, and your GPU also same. And then finally, once your hardware side, when your processor is ready, your GPU is ready, you are developing the OS software which can understand your hardware, and other softwares whatever you are developing, that has to communicate with your OS. Your OS in turn communicates with the hardware, and whatever the software you are developing, you are choosing one of the programming languages. Please mute. Please mute. So to develop any software on your classical computer, you are choosing any one of the languages, either Python or Java, and then you are developing the program. These are high-level languages. Your system can't understand, your CPU or GPU. And sure, you have to use the compiler and translate that into machine code, that is in form of zeros and ones. Then you can execute that on the classical computer. So this is the basic please mute. Please mute. Please mute. Hello.
So those who are unmuted, please mute it.
So this is the thing, like this is the base behind the classical computer. Now the basic how to build the quantum computer. Sir, one student is in not mute. It is not in mute state, sir. Now it is.
Okay, I will mute manually here. I will mute.
Yeah, thank you.
Okay.
So now to build your quantum computer, building a quantum computer is an incredibly complex, because it is going to deal with complex tasks and interdisciplinary, that requires deep expertise in physics, engineering, computer science. Okay, so all these concepts are required when you are building this quantum computer. We require people from physics background, we require people from engineering background, we require people from computer science background, and also all the interdisciplinary also is required while building this. So when you see the how to build this? We require qubits, quantum bits. Now, here, then we have this qubits. It represents 0, 1, and 0 and 1 simultaneously. That is superposition, and entanglement. That is combination of all that. If I want to design one 3-bit quantum computer, if I want to design, Bharat, please mute. Okay. If I want to design a 3-bit quantum computer, how many states will be there in that? 2 to the power of 3. So we have 8 states. So we can represent 8 states simultaneously. Okay. So a 3-bit quantum computer, which is 8 times faster than the 3-bit digital computer. Okay. Suppose if I want to design a 3-bit quantum computer, then that 3-bit quantum computer can represent 2 to the power of 3. That is nothing but 8 simultaneous states I can represent at a time. So your 3-bit quantum computer is 8 times faster than the 3-bit digital classical computer. So next we have to understand how to control these qubits. Okay, once you give the input, you have to control them and measure the output, and then readout system for that. Then cryogenics is required, because this I'll be explaining in further slide. Then we have to deal with quantum error correction. In quantum computer, one disadvantage is that it has high error rate when compared to your classical computer. Then quantum architecture scalability, then control systems and software. When you're working with your quantum computer, your controlling system, it's nothing but something similar to your OS software, and other software for developing all your other softwares for different purposes. Then material science, fabrication, interdisciplinary expertise, massive funding, and infrastructure. So to build the quantum computer, what and all is required? It is breakdown like this. Okay. Now, when you focus on qubits, quantum bits, this is a fundamental unit for your quantum computation. There are types of qubits: superconducting qubits used by IBM and Google, trapped ions used by IonQ and Honeywell, photonic qubits used by Zenodo, spin qubits in semiconductors like silicon, and topological qubits, theoretical, and by Microsoft. Now, when you are once you focus on the qubits, after choosing the qubits, now we have to control these qubits, and then you have to get the desired output by calculating. By using these qubits, you will do all the calculation, and you have to control these qubits to get whatever output you want, and then we have to measure that. So to control these qubits, now what you are trying to do, in case if you are working with this superconducting qubits, you are going to you have to manipulate these qubits, right? To insert, to get the output, you have to manipulate the qubits. To do some calculation using these qubits only, you can do it. So when you are manipulating that to get the desired output, then we need to measure that. So for that purpose, we have to choose this. You can choose microwave electronics for superconducting qubits. Okay, and if you're choosing this photonic qubits or ions, you can go with laser system. Then once you when you're working with this quantum computer, you have to control the software for pulse shaping, timing, error correction, and all. And then you have to finally you have to work with this cryogenic. What is this cryogenic amplifiers? Basically your quantum processor unit, whatever we are designing, that has to be manufactured at the lower temperature. Okay, so definitely if your QPU, that is quantum processor unit itself, is manufactured at the lower temperature. It is also known as cryogenic quantum computers. Okay, then all the other whatever the inbuilt basic units like cryogenic amplifier, all are also manufactured at the lower temperature only. This cryogenic amplifiers, it is used to read out the weak quantum signals. So this is the thing. First one is you are choosing the qubits, then you have to control the qubits. For that, you are choosing microelectronics or laser system. Then you have to use the controlling software for pulse shaping and all. Then you are using this cryogenic amplifier to read out the all the quantum signals. Then, as I said, your quantum processor unit, it is manufactured at the lower temperature. So most qubit, especially superconducting one, require extremely low temperature. Okay, and we require dilution refrigerator are used to reach this temperature. And since you are working with this cryogenic level, you require cryogenic wiring and shielding to reduce the thermal noise. As this quantum computer, it is prone to error. High error rate is there. Why? What is the reason? Because see, whenever you are when you start working with your qubits, they are fragile. They are prone to error. That we require error correction. Requires many physical qubits per logical qubit. It involves complex stabilizer code like surface code. Demands ultra low error rates, that is 10 to the power of -3. Finally, when you are with your QPU, that is your quantum architecture, you are designing the system that can scale to thousands or millions of qubits. Okay. Now, for example, if I say I am designing a quantum computer of 500 bits. Okay, that 500-bit quantum computer can represent 2 to the power of 500 simultaneous states. Okay, which is equal to something 10 to the power of 150 processor of classical computer. That is the computing power of your quantum computing when you compared with the classical computer. If you say I'm designing a quantum computer of 500 bits, it can represent 2 to the power of 500 simultaneous state at a time. Then the computing speed of that is, it is equal to 10 to the power of 150 processors classical computers. Okay, so finally, once you design all this, when you choose this, we need to interconnect them. Your qubits quantum computer, it is going to interconnected using fiber optics, microwave lines. Then your modular quantum architecture, it is going to interconnect for linking all the quantum modules. Then after once your hardware side, your CPU chip is ready by using all this concept. Now you are going to choose the software. That is your controlling software that is going to run on your quantum circuits and interface hardware. That is similar to your OS. Once your controlling software is ready, that can run on your quantum circuit. Now you can choose your quantum programming language like Qiskit, Cyric, Penele. All this you can use and you can develop your program on your quantum computer. Then since you know very well, your quantum gates also can understand only zeros, ones, 0, 1 simultaneously. These are the things that are represented in quantum computer. It can understand only zeros and ones. Definitely we require quantum compiler to translate all the programs that is developed in Qiskit or Cyric. Then finally we have the control hardware for real-time execution and feedback. Then material science and fabrication. Here in quantum computer, reliable, reproducible fabrication of qubit system. High purity material, low defect silicon sapphire is used. Non-fabrication facility like clean rooms are required for reducing the decoherence sources like two-level systems. Then when you are designing when you are building the quantum computer, the team should be consist of who are very good in physics, quantum physics, electrical engineers, RF engineers, cryogenic engineers. That means the circuit has to be worked at the low temperature. Okay, those people is required. Then software developers are required. Material scientists are required. Then theorists in quantum information and algorithms. All these are people are required. Expertise are required for building the quantum computer. Okay, then massive funding infrastructure is required finally for any, if you want to build your quantum computer, even prototype of the quantum computer is very expensive. It requires million to 100 millions in R&D. So this is the thing, all this is the conceptual overview for building your quantum computer. So if you focus on so finally, you have to choose the qubits, and you have to control the qubits, and then you have to modify, manipulate these qubits. You have to calculate. You should do all the calculation using these qubits. Once you do the calculation, you have to measure them. You require readout system. Then these systems are manufactured at low level, at low temperature. You should have cryogenics expertise things, and then it is prone to error, your quantum computer more. High error rates are there because as when your qubits are in usable states, okay, then it is fine. We say it is in coherent states. Once it starts interacting with the environment, it will go to decoherent state. That time the error, it is prone to more error. Okay, then you should know how to correct them. Then finally, you should focus on your quantum architecture scalability, and then the control system is nothing but similar to your OS, and the software you can develop using your quantum programming languages. And finally, all this expertise are required to manufacture, to build your quantum computer. Students, any doubts here? Okay. So next comes the fragility of the quantum system. Okay. So the fragility of the quantum system is one of the core challenges in operating the quantum computer. Here the conceptual explanation of the systems are fragile, like there are certain reasons why it leads to fragility. One is that decoherence, noise, gate errors, crosstalk, measurement errors. So all this will lead to causes for the fragility. Okay. Now, what is this decoherence? So usually, whenever your qubits are in usable state, okay, we say that it is coherent state. Everything is fine. Okay. When the qubit loses its quantum behavior due to interaction with the environment, for example, a stray photon or vibration can measure the qubit accidentally. Okay, that when then there will be collapsing in the state. The state will get collapsed. Okay, so that is known as decoherence. So whenever your qubits is interacting with the environment, they will go to decoherent state. Okay, so we can't avoid this. Okay, then when it is going to decoherent state, the information stored in the quantum computer will lead to error. So whenever the coherence time, whenever we measure, the qubit is in usable state, that is in microsecond or millisecond. If your qubit is in usable state, it is useful to us. That time it is known as, that time required to measure that usable state is also known as coherence time. As soon as when it start interacting with the qubits, start interacting with the environment, it will go to decoherent state. Okay, so we have to avoid that. So you can't avoid that, since definitely it will interact with the environment. Then whatever the information stored in the quantum computer leads to error. So this is one thing. So it is more fragility to the quantum system. Okay. Next is noise. The other cause for fragility is noise. The noise that is coming from the electromagnetic fields, thermal energy, cosmic arrays. Qubits can pick up this noise and flip the states, lose the phase, and correcting the computation. Okay. So this is the another thing. Gate errors. Quantum operations must be extremely precise, but there is a slight imperfection in the laser pulse or microwave signal that can lead to error. Then another error is crosstalk. Another cause for fragility is crosstalk. What is this? The operation on one qubit can unintentionally affects the nearby qubits. Okay, the operation of one qubit can unintentionally affects the nearby qubits. This problem will become more and more as you design the more complex quantum system. If you design more complex system for more super fast computation, that leads to dense computing system. Then the qubits will be very nearer. As the qubits are very nearer, the one operation on one qubit will affect the other qubit. Then also it will leads to error. Then finally the measurement error. Reading out the final state of the qubit is tricky, but you can accidentally collapse the state too early to get the wrong answer. Okay. So these are the reasons for the error. This is why your quantum computers has a high error rate, because of the characteristic of this. Like as I said that as the qubits are in usable state, it is known as coherent state. No problem, everything fine. Once your qubits start interacting with the environment, it will go to decoherence. Okay. Once it is going to decoherence means definitely we should interact. It has to interact with the environment. That state is known as decoherence. Then it will be whatever the information stored in the quantum computer, it leads to error. Okay, that we have to we have to take care. And then noise also should take care, and gate errors will be there, and crosstalk will be there, and definitely measurement error. So this is the fragility of the quantum system. Students, any doubts till here? So till now we covered two topics. One is building the quantum computer. Another one is fragility of the quantum systems. Hello.
Students, if you have any doubt, you can raise.
No doubts, ma'am.
Oh. Okay. Now tell me one thing. Now you know that very well. If I want to increase the computing speed in classical computer, what I should increase at the basic circuit level? If I want to increase the computing speed in the classical computer, okay, what I should increase at the basic level? Anyone? Your transistors at the basic level, your transistors we need to increase. As you increase the transistors, okay, your gates also will increase. Okay, then your computing speed also will increase. Can you tell me, if I want to increase my speed in my quantum computer, what I should increase? Anyone? We need to increase the qubits. Okay, as you increase the qubits, your speed of your quantum computer will increase. Okay, now for example, if I say that I'm designing one 3-bit quantum computer, definitely it will have 3 to the power of 3 states, that is 8 states. Okay, now if I want to double this speed of this 3-bit quantum computer, then how many bits I should increase? qubits? Students, my question is clear for you. The question is that in classical computer, if I want to increase the computing speed at the circuit level, I should increase the gates. If I increase the gates, in turn, it will increase the transistors. Okay. So as you increase the transistor at the base level, your gates will increase. Your computing speed also will increase. Whereas in your quantum computer, to increase your speed, you have to increase the qubits. Okay. Now, if I'm going to design if I'm going to build a 3-bit quantum computer, okay, how many states it can represent at a time? Two to the power of 3, that is 8 states. Okay, now if I want to double the speed of this 3-bit quantum computer, then how many qubits I should increase? Please note down this one. Next class you should answer me. Hello. Last class, when I took your last class, I asked you to find out whatever the AI tool developed in India. I want to know all those AI tool. I said, no. Have you checked? Students? Indian AI tools? Please answer this question. Unmute. One student unmute. Any one student? Last class I told you find out all the Indian programmers developed AI tools. Can you list out 1 or 2? Hello. Okay, at least you note down this question now. Okay. So in quantum computer, if you want to increase the speed, you have to increase the qubits. Okay. If I'm designing one computer, 3-bit quantum computer, if I want to double the speed, how many qubits I should increase? Please note down this. You answer me next class. Hello. Students?
Okay, ma'am.
Okay. What is the question? What is the question I told? Hello. If I'm designing a 3-bit quantum computer, if I want to double its speed, how many qubits I should increase? I want to know. Can you tell now? Just, it's okay. You can think on this. Anyone? Three-bit quantum computer, we can represent at a time 2 to the power of 3, 8 states simultaneously. Okay, it is 8 times faster than the classical computer, 8 times. Okay, now if I want to double the speed of this 3-bit quantum computer, I have to increase the qubits. How many bits I should increase? Okay, you note down this. The next class you tell me. Fine. Okay. Now next is condition for functional quantum systems. Okay. What is the condition for functional quantum system? One first condition is that very important is isolation. They need isolation. Without if there is no isolation, it is prone to more error. As you know that your qubit will be in usable state, that is known as coherence state. Okay, once your qubits start interacting with the environment, it will go to decoherence. It will prone to error. We are going to lose the information. So they are telling, when you're designing the quantum computer, isolation is very, very important. Okay, because when the quantum system must be shielded from its environment to preserve the coherent state. Okay, once it starts interacting with the environment, okay, it is going to decoherence. We are losing the information. due to the interaction with the fluctuation, electromagnetic noise, cosmic rays and all. So isolation is very, very important. We have to isolate your quantum system from its environment to preserve the coherent state. Otherwise, it leads to error. Once it is interacting with the environment, it goes to decoherent state and it is losing the information, whatever it is stored in the quantum computer. Okay. So the next condition is error management. As we know that quantum states are inherently fragile and error correction is very, very challenging there. Once because of noise, the error may occur. Because of your gate errors, the errors are occurring. Because of the crosstalks, one qubit, the operation on one qubit will affect the operation of other qubit. All these are the different errors. It is highly prone to error. So here what we are supposed to do that the no cloning theorem prohibits the duplication quantum states. Okay, and a fault tolerant operation requires keeping the physical qubit error rates below, and then the required overhead staggering each logical qubit may be needed. Okay, so because of these things, we are all this. It leads to we have to manage the all the errors. Okay, one is you have to isolate from the environment to reduce the decoherence so that we'll not lose the information. And next is we have to manage the error due to noise, due to your crosstalk, and due to the gate error. Next is scalability. The another condition for your building the functional quantum system is this is also very, very, very important. Scalability. When you're building your practical quantum system means scaling from tens to potential. So when you're increasing the qubit count, exponentially raises the
Ma'am, what is clone theorem?
Excuse me, ma'am.
Excuse me, ma'am.
Yes. One second. Yeah.
Excuse me, ma'am.
Yeah. Understood.
What is mean by clone theorem?
One second. Mute yourself. Mute. Okay. So what I'm trying to say that, see, since they're telling that your quantum states are highly inheritably fragile and error correction is both necessary and challenging. Here what they are trying, what is a cloning theorem? Forget about no cloning. What is cloning? What is cloning? You are trying to create a duplication, right? Cloning theorem is nothing but you are trying to create the duplication. The no cloning theorem is you are trying to prohibit the duplicating quantum state because complicating error correction strategies. Okay, so cloning means you are trying to duplicate. Here, the no cloning theorem, it will prohibit the duplicating quantum state. Okay. Hello. When you don't want to duplicate the quantum state, you should go with the no cloning theorem. Please mute. Okay. Please mute. Students. Okay. So if you want to manage your errors, you have to prohibit this no cloning theorem. Okay. That leads to we should avoid the duplicating quantum state, which may complicating the error correction strategy. Then we have to use the fault tolerant operation, requires keeping the physical qubit error rate below the threshold. Only then logical error rates be suppressed. Please mute. So one student asked me, what is this no cloning theorem? Whenever you want to create some duplication, we'll go with cloning theorem. But here they are telling you no cloning theorem, we will try to prohibit, it will avoid the duplicating the quantum state. Yes, because we should not complicate the error correction strategies, right? So only we have to go with, we have to prohibit this duplicating the quantum state. And also you're trying to follow, when you're designing your, when you're building your quantum computer, you're trying to follow this fault tolerant operation that keeps the your physical qubit error rate below the threshold. So these are the different concepts or conditions are used for functioning your quantum system that has been built. When you are managing the error, you have to follow all this. Okay, no cloning theorem prohibits the duplicating quantum state, fault tolerant operation to require keeping the physical qubit rate below the threshold. Clear? Then the required overhead is staggering. Each your logical qubit may need hundreds to 1,000 physical qubits, and real-time error decoding must outpace the qubit decoherence. Okay, so we need to manage the error because it is your quantum system is more fragile, it is more prone to error. We have to do all this. By using this no cloning theorem, you can avoid the duplicating quantum state. So that complicating error strategy, error correction strategies, we no need to complicate the error correcting strategies. Okay, all this you should follow. For error management, you are following all this. The next is another condition for your functional quantum computer is scalability. Okay, so whenever you are building a practical quantum system, means scaling from tens to potentially millions of qubits. So as the complexity of your computation increases, your qubits will be increasing. If you want more complex quantum computer, you should keep increasing the qubits. Okay, when you are increasing the qubits count exponentially, it raises the complexity and control. Then as you increase the qubit, to control also it will become more complex. Connectivity also will become more complex. How this qubit quantum computer for interconnection, they are using either microwave lines or fiber optics, right? That connectivity also increases. Then maintenance of coherence also will become difficult. Then physical infrastructure, the cooling system also is increases. So this is the one. Then the modular architecture, improved fabrication and photonic or topological qubit approaches offers a potential path forward. So whenever you are thinking that I want to increase the computing speed of my quantum computer, definitely you have to increase the qubits. Once you increase the qubits exponentially, everything, the complexity keeps increasing. For controlling your quantum computer, for connectivity also will increases, everything will increases. That is what the next condition. Okay, the stability. So when you are designing your functional quantum computer, achieving long coherence time and consistent operation is imperative. What is actually required when you are designing your quantum computer? We want long coherence time. That means your qubit in usable state, so that you get the your system is in operation. Okay, once it is going to decoherent state, you are losing the information. That is not your goal. Our goal is that our quantum computer should be in coherent state. That is, we should achieve the stability. Okay, the current NISQ devices holds from 50 to 1,000 qubits. Okay, but remain highly noisy and limited in algorithmic depth. Okay, enhancing gate and the architectural whatever the thing, they are able to achieve the stability, but again some trial and error is going on, because to achieve our ultimate goal is we want stability in the quantum computers. Okay, we want to achieve the long coherence time. Then the next condition for functional quantum computer system is that theoretical barriers. Okay, finally the quantum computing must grapple with the deep theoretical limits. Okay, the no cloning theorem restricts the error correction strategy. See, your cloning theorem, first of all you should know this cloning theorem. Cloning theorem means it is going to create the duplicates. So whenever I want to avoid the duplication in quantum states, the no cloning theorem can be used. This will restrict the error correction strategies. Then you can use this threshold theorem. Why this one? As we said that here, when you are using this fault tolerant operation, it requires to keep the physical qubit error rate below the threshold. So this threshold theorem they are following. Okay, to assure that below certain error rates, logical errors can be made arbitrarily small to make it small. But achieving and maintaining this threshold is non-trivial. Okay, so resource constraint, energy, bandwidth, one second, imposes ceiling on achievable computational accuracy even when theoretical error threshold exists. Okay, so we have certain resource constraint, energy, bandwidth, volume, this and all. It is imposing a ceiling on the achievable computational accuracy. Finally, our ultimate goal is whatever you are trying to compute, it should be with good accuracy, right? But there is some constraint on that because of the resource constraint like energy, bandwidth, and volume. Okay. So today we focused on our syllabus, that is building. One second. Building quantum computer, theoretical challenges and requirement. First, we focused on while building the classical computer, how the basic architecture is in quantum computer. When you build the quantum computer, these are the different breakdowns you should understand, from qubit to massive funding infrastructure. And any doubts in first this one on building the quantum computer? Any doubt is there on these particular points? While building the quantum computer, you are following all these points. Okay, qubits, qubit control, cryogenics, quantum error correction, quantum architecture scalability, control system and software, material science fabrication, interdisciplinary expertise, massive funding and infrastructure. Any doubts are there on this? These are the fundamental things you should know while building your, it's just a conceptual overview for building your quantum computer. Any doubts on these topics? Students? Hello? Any doubts on this? Yes or no? If you have any doubt on, if you,
No, ma'am.
no, okay. Now we'll go with this one. So once you build your conceptual quantum computer, by understanding all this concept, next is that they are telling your quantum computers are
No, ma'am.
okay. Fragility is there. The fragility of the quantum systems is, what are the causes for this fragility? One is decoherence. Can anyone tell what is this decoherence? Can anyone tell what is decoherence? One of the causes for fragility is in quantum system is decoherence. What it is? What is decoherence? Shall I tell once more? Yes or no? Or you will tell? Students, these points are clear. Decoherence, noise, gate errors, crosstalk and measurement error, causes for fluctuating. Okay, just an overview on this. See, whenever your qubits are in usable state, okay, that is known as coherent state. Everything is fine. You will not, all the information stored in quantum computer, it is usable to you. No, it is not prone to error. Everything you get, whatever you can access from the quantum computer. Everything is fine. So once your it is going to, your qubits is going to lose the quantum behavior once it is going to interact with the environment. You can't avoid this. It is unavoidable. Okay, that time what is happening, your information is going to lose whatever is there in the quantum computer. This is known as decoherence. Our main goal is that we have to maintain long coherence time, long usability of the qubits, that we have to achieve. But this is the basic problem. Okay, well, once it start interacting with the environment, it is losing the quantum behavior. Because you know why? Because see here, for example, X-ray photon. You know very well your quantum computer basics. It is depending on your quantum physics, isn't it? So X-ray photon or vibration can measure the qubit accidentally. So collapsing the states. One example I can say. So once it is starting, once your qubits interacting with the environment, it is going to lose the quantum behavior. So our goal is that we have to maintain long coherence time. But ultimately we can't do that. Once it start interacting with the environment, it is losing that coherence behavior. That is known as decoherence. Okay. So that is why your quantum systems are prone to high error rates are there in quantum computing. Other errors are due to this electromagnetic field, thermal energy, cosmic rays. It is there in our environment, right? So qubits will pick up that and it will try to flip the state. It will lose the phase. It will leads to correcting the computation. Whatever the calculation you are trying to do, there will be a correction in that. It leads to error. Okay, and this and all other than these errors in your quantum computer, gate errors will be there, crosstalk will be there, measurement error also will be there. Any doubt in this topic? Causes for fragility of quantum system. So one thing you should remember that my classical computer has very low error rate and it is operating at room temperature. Okay, whereas my quantum computer having high error rate because you know the reason why it is because of the characteristics of your the basics behind your quantum computers. As I said here, one example. When your quantum bit is in usable state, fine. Once a stray photon or a vibration can measure the qubit accidentally, it is going to collapse its states. Once it starts interacting with the environment, it is losing its states. Okay, that is the thing. That is the behavior of a qubit, right? Then finally, you have to keep them in the ultra cold temperature. Your QPU, that is quantum processor unit, you should maintain them at the ultra cold temperature. Okay, anything? Any doubts? So the causes for fragility is all this. Any doubts in decoherence, noise, gate errors, crosstalk, measurement errors? Yes, tell me faster. Yes or no? I'm ready to discuss on all these points. Causes for fragility in the quantum system. Any doubts on decoherence, noise, gate error, crosstalk, measurement error? Huh?
Measurement error.
Huh?
Please explain about measurement.
One student. Please mute. One student can ask.
Hello, ma'am.
Ah,
Ma'am, can you please explain about measurement error, ma'am?
okay. 1 second. Yeah. So see what you're trying to do whenever you want to solve any problem, you are going to give the input, right? Your inputs are in terms of qubits only 0, 1, or 0 and 1 simultaneously by using the concept of superposition and entanglement. Entanglement, you can give many possibilities at once. Okay, all this you are trying to give to your quantum computer, and then you have to do. You should keep varying your input until you get the desired output. Okay, as in classical computer, your output are very determined. In quantum computer, you can't get exactly, yes, I'll get like this. If I give this input, I'll get this. Because the thing is that here your qubits represent 0, 1, 0 and 1 simultaneously, and you are also using the entanglement. Then once you give this, you have to keep varying your input to get the output. So once you get the output, finally you have to read your final state of the qubit. It's very tricky. You have to manually adjust everything and then you'll get the output. Okay. So sometimes what happens? It may leads to error when you are doing the input side. When you are trying to tune your input, sometimes you can accidentally collapse the state too early, or you will get a wrong answer due to the noise in the readout. It may happen. When you are, see, when it is not like in a classical computer, you give the input, you get the determined output. Here, when you are try to keep changing the input because of your concept of superposition and entanglement, when you are changing your input at the input side, so at the time you may get correctly answer. Some noise will come because of to the environment, because of this electromagnetic rays or cosmic rays and all. Some disturbance will be there in the input, and then suddenly you may get some wrong answer. That is known as measurement error. Sometimes you may get correct answer, sometimes you may get wrong answer. So it is reading out the final state of the qubit is tricky. That is the basic your superpositioning and entanglement features are there. No, you try to give your input by modifying them, and you are representing all the states simultaneously. So that is the reason. When you are measuring your output, sometimes the noise may affect your input. That time the error may occur, or sometimes you get correct answer. Sometimes suddenly the noise is more, that electromagnetic rays or cosmic rays, your output little changes will be there. Okay. Hello. If you understood your module 1 correctly, that basics about your superpositioning and entanglement, this is very this point is very easy to understand. Any doubts? Hello. Shall I go to next one? Students? Shall I go to next one?
Yes, ma'am.
Okay. That is what they are trying to say. Because of the characteristics of this qubit, superpositioning and entanglement, and due to the noise and crosstalk, all this, your output when you are measuring, that may have some error. Sometimes maybe you may get correct answer, sometimes you may get wrong answer. That is why the trial and error is going on. They are working on this. Okay, this is one disadvantage in your quantum computer fragility. All the errors. Okay, so basically they are telling the next topic is conditions for a functional quantum system is that they want to reduce all the errors and they want to get the correct output. For that, condition is one is isolation. We have to isolate the quantum computer from the environment, so that you can have coherent state, long coherent state. Okay. If you have long coherent state, your information on the quantum computer, you will not lose that. Okay. Next is then next characteristics is next condition is error management. Since you know that due to all these reasons, decoherence, noise, crosstalk, gate errors, we have to manage the errors. So one is that they are telling you go with this no cloning theorem that may avoid the duplicating the quantum state, so that it will reduce the error correction strategies. Then use the threshold theorem, all that. Next is scalability. Another condition is scalability. What they are telling, if you want to increase your supercomputing speed of the quantum computer, definitely you should increase the qubits. Once you increase the qubits, definitely everything will become complex. To control the qubits also it is complex. Connectivity also complex. Maintaining the coherence also complex. Everything is complex. Finally, you require the cooling system to for this ultra cold environment is required for quantum computer. That is also you should provide. Next is stability. We have to maintain this long coherence time, but you know definitely it will interact with the environment. It will go to decoherence. You can't avoid that. People are working on this. Okay. And finally, your quantum computing must grapple with the deep theoretical limits. There are limits. Okay. The no cloning theorem restricts the error correction strategy. Threshold theorem assures the that below certain error rates, logical errors can be made arbitrarily small. They are following all this. Okay. So these are the things. Any doubts in this? Hello. Okay, students. Today we have covered three topics. One is building the quantum computer, conceptual overview. Second one is fragility of the computing your quantum computers. Then the causes for the fragility. Then we focused on the conditions for functional quantum system. Isolation, error management, scalability, all these theoretical barriers are the conditions for functional quantum system. Any doubts in this? So today, if you want to exactly understand the internally why this is and all happening, why it is so prone to error and all, your module 1 is there, that qubits, quantum physics, that base should be strong in you. Then these points are very easy to understand. Okay, we will end the session today. Any doubts? Any doubts? Okay, we will end the session today. Students. Hello. Should we end the session today? Any doubts are there on these three topics?
No, ma'am.
Okay, we will end the session. Okay, fine. So next class, okay, when you're coming to next class, I want last class I told you what. Hello, students. Last class I told you one question. Please mute. I told find out Indian AI tools. Indian AI tools. How many Indian AI tools you have worked on? For what purpose? I want some information on that. I told. Did you collect on that? Okay, when you're coming for next class, please. Can you list out? Can you list out Indian AI tools? but especially Indian programmers developed Indian AI tools. I want to know that when Chinese people are developing so many AI tools for all the purpose, we Indians, how many AI tools we have developed for what all purpose? I want to know. Did you find? Okay. So next class when you are coming, I want to know this answer for this question. Suppose if I'm designing a 3-bit quantum computer, okay, it can represent how many possible states? 2 to the power of 3, 8 states simultaneously at a time. Because of this, your 3-bit quantum computer, it is 8 times faster than the classical computer, 3-bit classical computer. Okay. Suppose if I want to double the speed of this 3-bit quantum computer, how many qubits I should increase? Next class, you should answer me this question. Okay. Because the basic is here, as you increase the qubits, your computation speed in quantum computer, you can increase. Okay. Whereas in your classical computer, if you increase this transistor at the circuit level, your computing speed can be increased. Here in quantum computer, if you increase the qubits, your speed can be increased. Okay. I want to know how many qubits you are going to increase to double the speed of 3-bit quantum computer. Okay, shall I wind up now? Any questions?
Students, if you have any doubt, you can raise. Otherwise, we'll close the session today. Madam, okay, madam?
Okay, sir.
No doubt.
Thank you, madam. Thank you, madam. We'll close the session now.
Yes, sir.
Thank you very much, madam, for giving today's session, a detailed session on building a quantum system. So it is very much useful for our students. Theoretically, they can have an idea about the quantum computer and its theoretical challenges and requirements. Okay, we'll see. We'll discuss further things in the next session, madam. Thank you. So we'll end up the session now. மேடம் எங்க அவங்க மாலத்தி அவங்க இருங்க வாங்க வாமா அங்க இருக்காங்களா? இங்க வந்தாங்களா இப்போ? சரி, பசங்களை அனுப்பிச்சு சொன்னாங்கன்னு சொல்லுங்க. க்ளோஸ் பண்ணிட்டு அனுப்ப சொல்லிட்டாங்க. ఓకే சொல்லிட்டு ఇన్ఫార్మ్ పెట్టండి. సిస్టమ్ షట్ డౌన్ చేస్తున్నారా? అట్లే మీకు మొబైల్ లింక్ ఆల్రెడీ సెండ్ వినోద్?
Yes, sir. Okay.